In the past few years, there's been an uprise of ARM processors. From Apple's M series chips to Qualcomm's new Snapdragon series of laptop processors, they're marketed as a brand new approach to personal computers and promise huge performance and power efficiency gains compared to traditional Intel and AMD CPUs, marking a great turning point in the world of personal computers. But what even are x86 and ARM? How do they differ and how did they end up competing only up until after 2020? Let's start with the beginning of it all. In 1978, Intel releases the 8086 chip, which becomes the brain of the first IBM PC. Because memory was expensive in the 70s, Intel wanted the code to be dense. The design philosophy was do more per instruction. Instructions could be complex, variable length, and do things like load from memory, compute, and store back into memory, all in one instruction. The philosophy was what would later be called CISC, or Complex Instruction Set Computing. Think of it like this: you want a sandwich, so you tell the chef just one single instruction: make a sandwich. The chef is built on the x86 instruction set architecture, or ISA, speaks the x86 language, so it only needs this one instruction to know all the necessary smaller steps, like cutting the bread, cooking the meat, and adding the vegetables. Later, IBM's decision to use the Intel 8088 in 1981 locked x86 into a positive feedback loop. Software was written for it, more PCs were sold, and there was more and more incentive to stick with x86. ARM, however, begins in a completely different context. Acorn Computers in the UK wanted a CPU for computers that was cheap, simple, and low power. The result was the Acorn RISC machine, or ARM, around 1985. The philosophy was simple: fixed length instructions, load store architecture, many registers, and simple decoding. This was what would later be called reduced instruction set computing. Think of it as asking, or rather teaching, a child to make a sandwich. You need to give them many simple instructions like open the fridge, grab the lettuce, close the fridge, and so on, until the sandwich is made. Programs running on ARM must provide all the most basic instructions to the CPU. The RISC concept provided good performance per clock, but absolute performance was modest at best, and the ecosystem was tiny compared to Intel's and IBM's. However, the two approaches to CPU design barely overlapped for more than 20 years. While x86 lived in desktops, laptops, servers, and workstations, ARM lived in embedded systems, industrial controllers, early mobile devices like pagers and phones, and later smartphones. The two architectures didn't even compete, and it wasn't just because of the performance. It was because of the entire context and the inertia of the computer chip market. Laptops, desktops, and servers didn't even need the energy efficiency of ARM, while embedded systems and controllers didn't need the power, the programs, and the ecosystem of x86. Moreover, ARM didn't even sell CPUs, it sold instruction set architecture licenses, CPU core designs, and reference implementations. This kind of customizability for the manufacturer of the CPU was going to be a huge advantage for the ARM instruction set architecture later. In 2007, the first iPhone revolutionized portable computing. After Apple, soon followed Samsung, Motorola, LG, and many other manufacturers. With smartphones, a new performance axis was created. Raw single-threaded performance was no longer the goal, but performance per watt was. Smartphones needed to be fast enough, but always on battery. This was catastrophic for the x86's traditional advantages. The ARM architecture had already been designed for this for over the last 20 years. Intel did try to respond with an x86-based Intel Atom processor. On phones like the first two generations of the Asus Zenfone, the processors were indeed fast and had the best single-threaded performance on the market, but they proved to be very inefficient on battery life, and the heat output was difficult to manage in the small form factor. Moreover, around 2012, quad-core ARM processors started appearing, which completely crushed the dual-core Intel Atom designs at the time. This is when ARM finally stopped being associated with embedded systems and started becoming a mainstream CPU architecture. Around 2012 to 2015 though, smartphones started demanding more and more processing power, while still being limited by the battery capacity. ARM designs like the Cortex-A57, A72, and A75 were no longer slow, mobile-grade chips. They were legitimate high-performance cores. This broke the stereotype that ARM-based chips were generally slow. In the following years, Apple, Qualcomm, Samsung, and MediaTek continued to push the envelope of ARM CPU performance with each yearly iteration, while maintaining excellent power efficiency. Still, ARM didn't directly compete with x86-based processors because all of this was still not enough to push RISC designs to the PC world. Gaming, video editing, and similar heavy tasks were still handled on wall-plugged PCs and laptops, so power draw was still not the main concern. To add to this, the most popular operating systems were still written for x86 CPUs. Compatibility and the ecosystem were keeping x86-based designs well anchored into the world of desktops and workstations, until Apple forced the issue. Because ARM-based chips could be built by anyone with a license, Apple managed to pull off an excellent example of vertical integration, with their iPhones and iPads, of course. With both hardware and software designed in-house, they could optimize their devices like no other company. This was obviously not true for the Macs, however, which still used Intel processors. With their A-series CPUs already showing industry-leading instructions per cycle and absurd performance per watt, Apple decided to take a leap of faith. In 2020, they released the M1 MacBooks. The first generation of Apple Silicon achieved something shocking. It matched or even beat the x86 CPUs, while using far less power and while offering excellent compatibility using Rosetta 2, which allowed running x86 code on ARM-based Macs with very little performance losses. Soon, program developers were forced to build ARM-native versions of their programs. Apple's strong position supporting ARM-based computers made it so that most programs on macOS are already natively built for Apple Silicon. The fact that macOS doesn't rely on legacy software also helped a lot, in contrast to Windows. Windows on ARM, however, was an idea of the 2010s. Microsoft's first serious attempt was Windows RT on ARM, which was a disaster due to being very slow and not supporting x86 programs at all. In 2016, Windows on ARM did bring 32-bit x86 app emulation, but it was still very slow and had poor driver support. Between 2019 and 2023, Qualcomm releases 3 generations of Snapdragon 8cx ARM processors for laptops, which are based on mobile designs and barely managed to reach the performance of Intel Core i5s of the time. The direction was good, but the release of Apple Silicon made Qualcomm's attempts feel unfinished by comparison. A major milestone for Windows on ARM was in 2021, when Microsoft finally added 64-bit x86 emulation on Windows 11 for ARM. Still, performance was only acceptable. Finally, the real competition to Apple's already 4-year-old run on ARM personal computers arrives in 2024, when Qualcomm releases the Snapdragon X Elite and X Plus CPUs, no longer based on old mobile designs and built from the ground up with the help of Nuvia and ex-Apple CPU architects. At this point, Windows 11 on ARM is also mature and is the first time a Windows ARM laptop feels like a normal laptop, just a lot more efficient and in some cases even slightly faster. But ARM-based CPUs didn't stop at the mobile segment of the computer market. With servers and data centers reaching enormous power consumption levels and struggling to cool down their CPUs, they too started using ARM-based CPUs made by companies like Ampere Computing or Nvidia. In the consumer market, desktops like Apple's Mac Studio use powerful chips like the Apple M3 Ultra to offer insane performance numbers in a very compact and quiet body. The future of x86 versus ARM is, however, still uncertain. At CES 2026, Intel revealed their new Panther Lake generation of laptop CPUs based on x86, showing impressive performance and battery life, which are solid competition even for the latest generation of ARM-based chips. Meanwhile, Snapdragon-powered laptops have not shown sales figures as impressive as the performance that they managed to achieve, indicating that maybe Windows on ARM was a little bit overhyped in the last few years. So in conclusion, no one knows what the future holds, but one thing is certain. The ARM instruction set architecture is now a solid competitor to x86. However, it may never fully replace it. For applications like gaming, x86 is still the superior platform, while ARM-based CPUs hold a big advantage in the mobile and server department. Well, that's about it for today. If you liked this video and found it interesting, don't forget to hit the like button. And if you want to see more videos like this, be sure to hit the subscribe button. See you in the next video.